Okay, so this is solids of known cross sections. All we're doing is we're changing the cross sections to triangles and semicircles. So triangles, we're dealing with half base times height. Usually they're right triangles. Usually they're isosceles right triangles, which means the base and the height are the same. So it ends up being half function squared. It's basically the half of a square. And then the semicircle. Semicircle is a little more complicated because if we put a semicircle with the base in that function in that coordinate plane where we have the footprint, so to speak, then from an axis all the way up to the function is the diameter. And we got that half circle dome coming up. So the equation for a semicircle is already half pi r squared, but the radius is half that distance. So it ends up being a quarter pi r squared. No, an eighth pi r squared, correction, because the radius is half of that distance and that's being squared. So yeah, 1/8 pi r squared. So just careful, take a little bit of time getting those area functions set before you integrate. You'll save yourself some headaches. But what you also find in terms of the area functions is everything everything is function squared. And then we have a multiplier out front. If it's a square, there's no multiplier, so it's 1. If it's a isosceles right triangle, it's a half because it's half a square. If it's a rectangle, then the multiplier for the rectangle shows up out front. It's a semicircle, then pi over 8 shows up in front. So it's a nice pattern. Take the time to kind of look at that pattern. So a couple of takeaways. It's important to know the direction of the slice. Is it perpendicular to the x or perpendicular to the y? Because that tells you have a dx or a dy problem. Take some time to find that area function with respect to the proper variable. Look at those patterns. They're cool. They are very neat. I totally geek out over them. But everything ends up being function squared in terms of the integrand. Make sure limits of integration match a proper variable. So if we're going perpendicular to the y, then we're stacking them in the y direction. And same with the x. Okay, so how can we adapt our knowledge of calculating area so that we can calculate volume? Same essential question as we started this known cross-section section about. So we're replacing the function. It's the same answer. We're replacing that integrand, that function, with an area expression. Okay, so we've got some topic questions, and then we've got day 9 notes for Wednesday. And then there's just one con for tonight. So you can go ahead and get started on that.